Imagine diving into a world where lakes float inside the ocean, where underwater chimneys rise like glowing marble castles, and where an entire layer of animals moves up and down every day so perfectly in sync that early sonar operators thought the seafloor itself was trying to escape. A world where ancient polygons carve themselves into the Atlantic mud like geometry homework left behind by the planet, and where whirlpools in Antarctica trap water for years just because they feel like procrastinating, where the loudest sound ever recorded underwater turns out to be maybe ice or not, where volcanoes explode with such cosmic enthusiasm that they make the atmosphere ring like a bell. And all of this, every strange portal, every luminous creature, every inexplicable rumble, still hides more questions than answers. Today, we're traveling into the deep ocean's strangest corners, the places even science looks at and says, okay, what? From blue holes that behave like vertical trapdoors to rivers of darkness flowing miles beneath the waves, this is the story of the ocean's most baffling mysteries. Each one a reminder that our planet is far weirder, wilder, and more spectacular than we ever imagined. So take a deep breath, because after this dive, you'll never look at the ocean the same way again. If you ever want to feel both incredibly tiny and profoundly confused, just stare into the ocean long enough. Not the friendly part where beach waves politely nudge your ankles, but the real ocean, the one scientists describe with a tone normally reserved for haunted houses. Because down there, past the point where sunlight gives up and turns back toward the surface like, nope, not going any farther, lies a world so bizarre that even with all our modern tools, we still understand only a sliver of it. And that sliver is the equivalent of licking the frosting off a cake and calling yourself a baker. The ocean holds mysteries that laugh at our satellites, shrug off our submersibles, and toss our expectations into the abyss like a bored dolphin throwing a seashell. Imagine this. Humans have mapped the surface of Mars, the Moon, and even parts of distant asteroids with better resolution than the majority of Earth's seafloor. That is right, space, the place that is literally space, is easier for us to chart than the waters wrapping around our own planet. It is like knowing your neighbor's entire family tree, but not knowing what is in your own basement. And to be fair, the ocean's basement is a lot scarier. There are trenches so deep that if you dropped Mount Everest into them, the peak would still sit underwater like it did not meet the dress code. There are regions where the pressures get so extreme they squeeze objects, the way life squeezes your soul on a Monday morning. And through every attempt to explore these areas, the ocean maintains the same attitude. You may look, but I am not explaining anything. We build robots tougher than tank armor, only to watch them descend into darkness and return with footage that raises more questions than answers. Scientists analyze sonar readings that come back looking like abstract art created by someone who has never seen an art class. Even sound behaves strangely down there, warping and bending through the water in ways that make noises echo for miles. The ocean seems to enjoy acting like a funhouse mirror for science. Everything gets distorted, stretched, or hidden entirely until we start wondering whether the ocean is messing with us on purpose. But here's the thing that makes this whole story truly fascinating. every time we do manage to navigate these uncooperative waters, every time we poke our curious little noses into the depths, the ocean rewards us with glimpses of things so strange they feel fictional. Entire ecosystems thriving without sunlight, creatures that glow like biological neon signs, geological structures that bend our understanding of what is possible on Earth. It is as if the ocean is saying, "You want answers? Sure. But you are going to have to work for them, and I might throw in an existential crisis or two for free." And so we keep trying. We keep building stronger submersibles, smarter sensors, and scientific instruments that basically amount to politely asking the ocean to please, just this once, cooperate. And sometimes it does, just long enough for us to realize that whatever we thought we understood is either incomplete or hilariously wrong. If scientists had a motto for deep sea research, it might be, well, that is interesting and concerning, and also probably not what we were expecting. This is where our journey begins, in this overlapping territory between what we know, what we think we know, and what the ocean casually hides like a dragon sitting on a treasure trove of geological confusion. Over the next chapters, we will travel into blue holes that plunge deeper than logic suggests possible, lakes that sit inside the ocean like Russian nesting dolls of salt, volcanic chimneys that rise like underwater cathedrals, and dark zones where animals live in conditions that would make most life forms crumble. But before we dive into those unexplainable places, we sit here together at the surface, squinting into the waves and wondering how something so enormous can still be so mysterious. You would think that after thousands of years of sailing, exploring, measuring, mapping, and occasionally panicking, we might have a solid grasp of what is happening under there. But no, the ocean remains a master illusionist, a place where data goes to get confused and strange anomalies appear just long enough to prompt heated debates at scientific conferences. It is the one realm on Earth where the phrase, "we do not know yet," gets used so often it could be printed on lab coats. And maybe that is exactly why the ocean captivates us so much. Not because we understand it, but because we absolutely do not. Humans are naturally curious creatures. We poke things with sticks. We press buttons labeled, "Do not press," and we stick cameras into places with warning signs. The ocean is the ultimate version of that forbidden button. It dares us to ask questions and then hides the answers just out of reach, like a cosmic prank with 1,000-foot waves. So as we begin this journey through the places in the ocean we still cannot explain, remember one thing: the mystery is the point. The strangeness is part of the fun, and if at any moment you feel confused, startled, or mildly concerned for the future of human understanding, congratulations. That means you are finally thinking like an oceanographer. If you have ever stared into a deep puddle and felt an unreasonable amount of fear that it might swallow you whole, congratulations. You already understand the emotional vibe of a blue hole. These circular, impossibly dark pits scattered across the ocean floor look like someone took a giant cookie cutter to the seafloor and forgot to mention why. From above, they appear almost too perfect, as if Earth tried its hand at minimalist design and decided a few massive ocean potholes would really tie the place together. But the unsettling part is not their shape. It is the way they drop straight down, plunging into darkness like nature accidentally left open a trapdoor. Blue holes are vertical caves, often carved during ancient times when sea levels were lower, and these caverns were part of dry land. Over thousands of years, rising water quietly filled them up, leaving behind a kind of geological surprise party for modern explorers. And the ocean loves a good surprise party, because once divers venture inside, they find features that feel like they were designed by an over-caffeinated dungeon master. Narrow passages, harsh chemical layers, complete darkness that swallows flashlight beams like a picky eater rejecting vegetables. The only thing missing is a glowing treasure chest and a dramatic soundtrack. One of the most famous of these is the Great Blue Hole in Belize, a nearly perfect circle roughly the size of a small town. From the surface, it looks calm and serene, but descend a little, and you enter a world that seems physically allergic to friendliness. The walls drop sharply, then open into a massive cavern decorated with stalactites. Yes, stalactites underwater, meaning these formations grew back when this cavern was exposed to air. It is a quiet reminder that Earth is always changing, sometimes gently, sometimes in the "I'm flooding your cave now, good luck" kind of way. But the strange beauty of blue holes is not just their architecture, it is the chemistry. For reasons that make scientists squint at their equipment and double-check their oxygen tanks, many blue holes contain layers of water that refuse to mix. Imagine pouring syrup into a glass of water, except instead of syrup, it is hydrogen sulfide, and instead of a glass, it is a death pit in the ocean floor. These layers create sharp chemical boundaries. One moment you are swimming in normal seawater, and the next you are crossing into a layer so murky and toxic that it looks like the ocean's version of a mood swing. The smell alone is enough to make even seasoned researchers reconsider their life choices. Hydrogen sulfide has the scent of rotten eggs, which is impressive considering there are no chickens within miles. Why these layers form is partly understood. Bacterial activity, restricted flow, and trapped organic material all play a role. But the exact conditions that produce such sharply defined chemical zones remain a puzzle. Blue holes often act like pressure cookers of trapped ancient water, brewing up chemical mixtures that are almost never seen in open ocean environments. Scientists find themselves collecting samples with the enthusiasm of someone discovering a new flavor of soda. Except this soda can dissolve metal and is extremely offended by oxygen. And then there is the life inside them, or rather, the suspicious lack of it. Many blue holes are biological deserts past a certain depth. Fish will swim near the opening, peek inside, and metaphorically shrug like, "Nope, that's a you problem." Some microbial communities do thrive here, but they tend to be extremophiles, organisms with the kind of can-do spirit that lets them live in places where everything else dramatically dies. They munch on sulfur, tolerate impossible conditions, and generally behave like microscopic overachievers. Scientists love these microbes because they may offer clues to what life could look like on planets with atmospheres more hostile than a customer service phone menu. But perhaps the strangest thing about blue holes is how frequently we keep finding new ones. Just when scientists think they have cataloged the major ones, sonar scans reveal fresh pits hiding in remote corners of the ocean. Some are massive, others strangely narrow, and a few appear connected to underwater tunnels that stretch farther than anyone expected. These tunnels are a particular source of argument. Some researchers suggest they are natural erosion channels. Others suspect ancient flooding events carved them open. A few divers swear that certain passages feel like they lead somewhere important, but they also admit that swimming into an unexplored underwater tunnel ranks somewhere between extremely reckless and please do not do that again. Even the blue holes near coastlines remain frustratingly unexplained in certain ways. For example, some of them contain trapped sediments that do not match the surrounding geology, as though materials traveled there from unknown sources. Others show signs of sudden collapses, suggesting dramatic events in the geological past that we still do not fully understand. It is like looking at a crime scene where the culprit is erosion, time, chemistry, or possibly all three working together in a suspiciously coordinated way. What makes blue holes especially haunting is their silence. Sound behaves strangely inside these caverns. Voices and bubbles echo unevenly, disappearing into side chambers or fading into the heavy water layers. Divers describe the sensation as eerie, almost like the cave absorbs noise on purpose. And when you are suspended in vertical darkness, descending past layers of increasingly hostile chemistry, the last thing you want is silence with dramatic timing. Yet even with the risks, blue holes remain irresistible to scientists because they offer something the ocean rarely does: a contained environment, a place where ancient conditions still linger, a window into chemical processes that shaped our planet long before humans arrived with boats and curiosity. They are both dangerous and invaluable, like natural laboratories protected by geological booby traps. These places are not here to make sense. They are here to remind us that Earth has had billions of years to experiment with its own terrain, and not all results were designed with human expectations in mind. A blue hole is the ocean's way of saying, here is something incredibly interesting, but also please do not fall into it. If you were to take a submarine into the deep sea, glide over the seafloor, and suddenly see what looks unmistakably like a shimmering lake, complete with waves, shorelines, and maybe even the psychological urge to dip your toes in, it would be understandable to think your vessel has sprung a leak, or perhaps you are hallucinating from too many hours without sunlight. But no, you have just encountered a brine pool, the ocean's most dramatic attempt at creating a body of water inside another body of water. Like nature accidentally layered two worlds on top of each other and shrugged as if to say, let's see what happens. Brine pools are essentially underwater lakes so salty that they behave like a separate liquid entirely. Their salinity can be 5, 10, even 8 times higher than the surrounding seawater. Imagine a cup of water. Now imagine pouring an entire bag of salt into it, then another bag, then a third. Eventually, the water gives up on the concept of dissolving salt and becomes its own entity, heavier, denser, and ready to sink to the lowest point available, which is exactly what happens on the seafloor. The result is a thick, syrupy layer of hypersaline water that refuses to mix with the ocean around it, creating the illusion of a lake sitting peacefully at the bottom of the sea like it owns the place. The edges of these pools often form distinct rippling boundaries known as haloclines, where the two waters meet but do not blend. It is the ocean's equivalent of watching oil hover above vinegar, only far more ominous and much less appetizing. Submersibles that cross into this layer wobble, tilt, and struggle like they suddenly forgot how physics works. Even their cameras will show a warped, shimmering distortion that looks suspiciously like you are watching reality buffer. Now, if you are a fish and you accidentally swim into a brine pool, your day is about to go poorly. The dense, salty water is so harsh that it essentially pickles anything that breaches the boundary. Fish sink, thrash briefly, and learn a one-time lesson about the importance of reading the "do not enter" signs that nature did not actually put up, but probably should have. For this reason, the shoreline of a brine pool is often lined with the unmistakable remains of unlucky creatures that wandered too close. Scientists describe these scenes with words like mortality rim, which is polite scientific language for "this is where all the bad decisions ended." Yet as deadly as brine pools are to most forms of life, they are also some of the most biologically intriguing places in the ocean, because within this lethal cocktail of salt and toxic chemicals, often rich in methane, hydrogen sulfide, and other substances that would send normal organisms into immediate retirement, there exist thriving microbial communities. These microbes survive without sunlight, oxygen, or any of the typical comforts life seems to enjoy. Instead, they metabolize chemical compounds from the brine, turning poison into nourishment with the enthusiasm of organisms that never got the memo about how life is supposed to work. These microbes form thick mats along the edges of brine pools, resembling fuzzy carpets or alien quilts that ripple with movement when currents shift. Scientists adore these creatures because they offer a glimpse into the kinds of life that might exist on other planets or moons with equally weird conditions. If microbes can thrive in a place where water is essentially liquid salt, sludge seasoned with toxic gas, then life elsewhere in the universe suddenly feels a lot more plausible. But brine pools are not only microbial wonderlands, they are also geological puzzles. Many form through the collapse of salt domes, massive underground deposits left behind by ancient oceans that evaporated millions of years ago. Over time, the salt within these formations dissolves and seeps upward, mixing with seawater until it reaches concentrations high enough to create a brine pool. In other regions, gases like methane bubble up from deep sediments, altering chemistry, shifting pressure, and creating perfect conditions for hypersaline lakes to emerge. Each pool is like a chemistry experiment Earth has been conducting for ages, without supervision, safety goggles, or regard for human confusion. Some brine pools even have currents. Yes, currents. Rivers flowing inside the ocean, carrying dense brine from one depression to another, carving channels that look suspiciously like riverbeds. Submersibles have filmed these brine rivers winding along the seafloor with miniature banks and waterfalls, defying intuition and biology in the most theatrical way possible. There is something mind-bendingly surreal about watching a submarine drift above an underwater waterfall. It feels like cheating on reality. But the mystery of brine pools does not stop at their odd structure. Researchers studying them are still trying to understand why some pools appear stable for thousands of years, while others shift unpredictably. Certain pools expand, others shrink, and a few seem to vanish over time as if they decided to relocate for better scenery. The chemistry inside them can change too, sometimes gradually, sometimes abruptly, leaving scientists scratching their heads and updating their data with the resigned sigh of people who know the ocean likes to improvise. There is also the question of what secrets these pools might be preserving. Because brine is so dense and isolating, anything trapped within it decomposes extremely slowly. Microbial DNA, chemical signatures, even geological clues can remain preserved far longer than in normal seawater. Some scientists think brine pools may hold records of ancient environmental conditions or microbial lineages that have evolved in near isolation, untouched by the rest of the planet. If the ocean had a filing cabinet full of strange ancient documents, the brine pools would be the drawers labeled "Do not open unless ready for confusion." And perhaps that is why brine pools continue to captivate researchers. They are equal parts mesmerizing and menacing, quiet, glassy lakes that tempt explorers with their beauty while whispering, "Do not touch, I will absolutely ruin your equipment." They are places where physics behaves reluctantly, chemistry does whatever it wants, and biology performs stunts that feel like cheat codes. In a world where we often assume we have seen everything water can do, brine pools step in and remind us that the ocean still has layers of weirdness waiting patiently on the seafloor. Lakes beneath the sea, rivers beneath those lakes, and within them, life that refuses to play by the rules. If the deep sea ever opened a wellness resort, the champagne vents would be its signature attraction, at least until guests realized the bubbles were not exactly the soothing, fizzy kind you find in a hot tub, but the touch this and your tissues dissolve faster than an antacid tablet kind. These vents, discovered near volcanic arcs in places like the Western Pacific, are geological oddities that spray out shimmering streams of liquid carbon dioxide. Yes, liquid carbon dioxide. The stuff you find in soda, except here it is under so much pressure that it refuses to stay a gas and instead bubbles out like the ocean decided to carbonate itself. At first glance, these vents really do look inviting. Submersible cameras capture what appears to be a gentle, silvery bubbling, almost festive, as if the earth is hosting a deep sea celebration. But the festive mood evaporates quickly when you learn that dipping your hand into this stuff would be like volunteering to be marinated. These vents reach acidity levels that would make vinegar blush. They create pockets where the pH drops so sharply that even metal equipment begins to corrode like it is auditioning for a Rust documentary. It is the kind of setting where any creature that wanders in unprepared immediately revises all of its life choices. And yet, as always, the ocean loves contradiction. Because despite these vents existing in what can only be described as underwater death jacuzzis, life still gathers around them. Not the kind of cheerful, colorful life you find in coral reefs. No, this is the gritty, we will thrive anyway kind of existence. Some microbes cling to nearby rocks and metabolize the carbon dioxide with the determination of creatures that have never known a comfortable day in their lives. These organisms are fascinating because they operate on biochemical pathways that are not common in typical marine environments. Studying them gives scientists valuable insights into early Earth, when the atmosphere and seawater chemistry were dramatically different, and life had to tolerate conditions that would now send most organisms into instant retirement. But before we get too deep into the biology, it is worth appreciating just how strange the physics of these vents are. Carbon dioxide does not turn into a liquid under normal oceanic conditions. It requires a bizarre combination of low temperature and high pressure, conditions you rarely get simultaneously unless you venture deep enough for the water above you to weigh more than several skyscrapers stacked on top of each other. At depths like these, gases behave more like confused liquids. They do not quite flow like water, but they also do not expand the way gases normally do. Instead, they slither upward in shimmering blobs, forming bubbles that wobble and distort like transparent jellyfish. Watching these bubbles rise is mesmerizing. They refract light in ways that make them appear silvery, as though each carries a little mirror inside. When they break apart, they release wisps of carbon dioxide that dissolve rapidly and drop the surrounding pH even further. The area around the vents becomes a chemical minefield. Micro pockets of acid so strong that they create miniature gradients in the water. A delicate shift to the left might be tolerable. A tiny drift to the right, and the acidity spikes into, please do not breathe this, touch this, or think too closely about this territory. The geology powering these vents is equally mysterious. They occur along cracks where magma lurks beneath the seafloor, heating water and altering its chemistry until minerals dissolve into it like ingredients in a stew. But unlike typical hydrothermal vents, which release hot, mineral-rich fluids, champagne vents eject something far stranger. Scientists suspect that deep beneath the surface, carbon dioxide gets trapped in liquid form inside rock pores. When tectonic forces shift, sometimes violently, sometimes subtly, these pockets open, allowing the liquid CO2 to escape upward like fizzy ghosts. One of the most remarkable champagne vent fields lies near an undersea volcano, known for its unpredictable temperament. This volcano has a habit of erupting with alarming enthusiasm, sending plumes of ash and lava into the water. After these eruptions, the vent fields often shift. New openings appear. Old ones disappear. Some vents pulse rhythmically, releasing bursts of carbon dioxide every few seconds, almost like the seafloor has developed a heartbeat. Others form long, continuous streams that feel eerily similar to underwater fireplaces. If fireplaces could melt calcium shells on contact. That shell-melting ability is one of the most dramatic features of champagne vents. Animals with calcium-based exoskeletons, like clams or crabs, cannot survive close to the vent openings because the acidic water dissolves their shells. This creates a biological sorting zone where only creatures with soft bodies or specialized adaptations can get near the vents. It also offers scientists a natural laboratory for studying how marine ecosystems might respond to ocean acidification on a wider scale. Because if you want a preview of what high carbon dioxide levels can do to seawater, the champagne vents are essentially running the world's most intense simulation. Even more puzzling is the temperature. Unlike many hydrothermal vents that blast out boiling fluids, some champagne vents are surprisingly cool. They are like the quiet sibling of the vent family, less flashy, but far more chemically eccentric. These cooler temperatures allow liquid carbon dioxide to remain stable, which only makes the whole environment feel stranger. It is one thing to encounter deadly acid spas. It is another to encounter deadly acid spas that feel like they should be refreshing. Divers and submersibles approach these vents with extreme caution. The carbon dioxide can displace oxygen in enclosed spaces, creating dangerous pockets where breathable air suddenly becomes a luxury. Robotic arms must be coated with materials resistant to corrosion. Cameras need protection from acid pitting. Every movement must be deliberate, because even a small plume of liquid CO2 drifting toward equipment can cause damage that sends engineers into that special kind of spiral usually reserved for tax season. And yet, despite every warning sign, these vents remain enthralling. They show us that Earth still runs experiments beneath the waves, quiet, continuous experiments in chemistry, biology, and geology that we barely understand. Champagne vents remind us that what looks beautiful can also be lethal, and what looks hostile can still sustain life. They are underwater irony at its finest, bubbling with danger, mystery, and just enough sparkling menace to keep scientists coming back for more. If the ocean had a nope zone, a place so remote, so hostile, and so spectacularly uninterested in human curiosity that even the bravest submarines hesitate, Serena Deep would be it. Tucked within the Mariana Trench, this pocket descends to roughly 10,900 meters, though the exact depth shifts depending on who measured it, what equipment they used, and how much the seafloor felt like cooperating that day. Depth in Serena Deep is like the trench's version of mood swings, dramatic, unpredictable, and scientifically inconvenient. To understand the magnitude of this place, imagine stacking 30 Eiffel Towers on top of each other, then sinking them into the ocean until even the top one cannot see sunlight. Or imagine the pressure more than 1,000 times what you feel at sea level. A pressure so intense that it does not politely push. It compresses, squeezes, and annihilates with the enthusiasm of a hydraulic press trying out for a talent show. At that depth, metals bend, electronics malfunction, And anything with air pockets is about as welcome as a balloon in a black hole. If an unprotected human somehow appeared there, they would not even get the chance to gasp in horror. Survival time would be approximately there and gone, with absolutely no punctuation. Serena Deep sits southeast of the trench's main axis, and unlike the more famous Challenger Deep, which has enjoyed a decent amount of media attention, Serena remains the mysterious middle child. It does not get documentaries. It does not get tourist submersibles. It does not get James Cameron. Instead, it gets brief visits from specialized landers and robots that drop in, record a few minutes of baffling data, and then scramble back to the surface, like they have just witnessed something they cannot emotionally process. Part of the problem is access. The trench walls in this region are steep and unpredictable, sculpted by eons of plate tectonics grinding together like two continental scale teeth. The Pacific Plate dives beneath the Philippine Plate here, plunging diagonally downward and dragging the sea floor with it. The result is a jagged, complex landscape where sediment avalanches, shifting ridges, and sudden drop-offs are not special events. They are Tuesday. Anything lowered into Serena Deep must navigate terrain that looks like it was designed by gravity having a tantrum. The water itself is bizarre. It is near freezing, yet it remains liquid because of the immense pressure preventing it from turning into ice. The entire environment is a tangled stack of contradictions. Low temperature usually slows chemical reactions, but this deep, pressure-packed environment speeds certain reactions up. Sound travels faster here. Water becomes denser. Even molecules behave differently, jostling against each other in tight, claustrophobic dances. If you could somehow bottle Serena Deep water and bring it to the surface without the pressure changing, which you cannot, it would burst violently as the trapped molecules expand. It is the oceanic equivalent of opening a soda that has been violently shaken for several million years. And then there is the sediment. Thick, soft layers of fine particles settle over the basin, drifting down from far above in a slow, constant rain known as marine snow. But in Serena Deep, this snow accumulates in strange patterns. Some areas feature dramatic depressions, while others appear unusually smooth, as though something has swept across the seafloor. Scientists are not sure whether these textures come from seismic events, underwater landslides, or the trench simply rearranging its interior decor. The bottom line, Serena Deep looks deceptively still, but everything beneath the surface is moving, slowly, relentlessly, and without a trace of concern for research schedules. Despite the crushing pressure, life exists here, not the kind with eyes, fins, or even the faintest desire to be seen on camera, but life nonetheless. Microbial organisms inhabit the sediments, metabolizing chemical compounds that seep up from the depths of the Earth's crust. These microbes are tough on a molecular level. Proteins adapted to pressure that would shred ordinary cells, metabolic processes that function in harsh darkness, and membranes that resist collapse. To survive here is to evolve beyond the limits of what we normally consider possible. Every so often, researchers catch glimpses of larger organisms too, not the kind that spark nightmares or tabloids, but small, resilient animals like amphipods, shrimp-like crustaceans that seem to fear absolutely nothing, including depths that would pulverize most biological structures. The fact that these creatures thrive where humans cannot even send a submarine without stress testing. Every bolt is both inspiring and slightly embarrassing. One of the greatest mysteries of Serena Deep is how little we know about its geology. While scientists have mapped small sections, most of the basin remains a blurry patch on sonar images, as though even the instruments do not want to get too close. Some regions appear to host deep cracks that may connect to fluid systems below the crust. Others hint at unusual mineral compositions. There is even speculation, just speculation, that certain areas could house supercritical fluids, substances that are neither liquid nor gas, behaving instead like dense, heated hybrids found in the most extreme geological environments. If true, it would make Serena Deep not only a pressure cooker, but also a natural laboratory for exotic chemistry. And that is what keeps pulling scientists back. The possibility that something entirely new lies hidden beneath those kilometers of water. Something about the physics, chemistry, or biology of Serena Deep may rewrite what we think we know about Earth's limits. But every attempt to explore it comes with the ocean's quiet reminder that some places are not easily persuaded to reveal themselves. Serena Deep is not just deep, it is defiantly deep. A place where pressure rules, light is banished, and the laws of nature stretch into unfamiliar shapes. A reminder that even on our own planet, there are realms so alien that visiting them feels less like exploration and more like trespassing. And somewhere down there, beneath unfathomable weight and absolute silence, the deepest secrets of Earth wait with perfect patience. If the ocean ever auditioned for a science fiction movie, the Baltic Sea anomaly would be its dramatic entrance, sliding onto the stage with the confidence of a creature determined to get people talking. Discovered in 2011 by a team of treasure hunters using side-scan sonar, this strangely shaped seafloor formation instantly became the kind of headline that makes scientists sigh and conspiracy theorists install new wallpaper on their bedroom walls. The sonar image showed what appeared to be a massive, rounded structure with crisp edges and unnervingly straight lines, as if someone had gently parked a flying saucer on the seabed and then wandered off to run errands for a few millennia. The anomaly sits roughly 90 meters beneath the surface, not too deep by ocean standards, but just deep enough to make visual investigation inconvenient and underwater rumors extremely efficient. Early sonar readings revealed a disc-like shape around 60 meters wide, resting at the end of a long, oddly flat formation, sometimes described as a runway. If that phrase makes your brain begin assembling alien pilot theories, you are not alone. Millions of imaginations sprinted directly into science fiction territory. Media outlets happily fanned the flames, floating ideas ranging from crashed spaceships to ancient temples to technology left behind by a civilization that apparently decided Scandinavia was the perfect storage unit. But reality, as always, quietly wiped its glasses, reminded everyone to breathe, and pointed out that sonar images can make rocks look suspiciously well organized. Side-scan sonar is excellent for spotting shipwrecks, pipelines, and curious lumps on the seafloor. But it also has a weakness. It sometimes turns perfectly ordinary geology into a blurry Rorschach test. What you see in a sonar image often depends on how much sleep you have had and how many science fiction movies you have watched lately. When divers finally visited the site, they found something far less shiny than the imagined alien craft. The formation is rough, grainy, and covered in a coating of sediment that would make even the most advanced spaceship look like a poorly maintained patio. The structure does have some strange geometric qualities: flat surfaces, sharp angles, and what appear to be broken off pieces resting nearby. But these details, instead of supporting extraterrestrial theories, point more convincingly toward geological processes. Nature may not design intentionally, but it does enjoy experimenting with shapes that confuse humans. The anomaly rests in a region that was dramatically shaped by glaciers during the last ice age. As enormous sheets of ice advanced and retreated, they scraped, carved, polished, and dropped off enormous blocks of material. The Baltic Sea is essentially a gallery of glacial leftovers, featuring everything from smoothed bedrock to piles of erratic boulders that glaciers dragged across great distances before abandoning them like uninterested toddlers. It is entirely plausible that the anomaly is one of these glacial deposits, maybe a piece of bedrock that was fractured, moved, and then sculpted by time into its current eye-catching shape. But here is what makes the anomaly genuinely intriguing rather than dismissible. It does not quite match any single explanation perfectly. Some of the rock appears unusually smoothed, almost industrial in texture. Certain edges are straighter than expected for random glacial debris. The runway leading to it is puzzling, a long ridge that looks too tidy to be accidental, yet not tidy enough to declare it the handiwork of intelligent beings, unless those beings were extremely sloppy or in a hurry. Geologists who examined samples reported that parts of the structure are composed of granite, basalt, and sandstone, common rocks in glacial regions. But they also found minerals like limonite and goethite coating the surface, which led to a burst of speculation, because these minerals sometimes form through biological or metallic processes. This, of course, sent conspiracy circles into full celebration mode. "See?" they shouted. "Alien rust!" Scientists, on the other hand, pinched the bridge of their nose and explained patiently that these minerals can form naturally under the right chemical conditions in seawater. Nature may not be an alien engineer, but it is exceptionally good at making ordinary things look exotic. What truly complicates matters is the structure's overall symmetry. Humans are pattern-seeking creatures. We see faces in clouds, animals in toast, and cosmic messages in random noise. So when the Baltic Sea anomaly presents an unusual curve here, a flat angle there, and a peculiar ridge leading up to it, our brains immediately assemble the pieces into something familiar: a ship, a building, a machine, anything but a rock, doing its best impression of a mysterious artifact. Even sonar rescans over the years have changed the shape slightly. Subtle differences in angle, resolution, and sediment coverage produce dramatically different outlines. In some scans, The anomaly looks circular and clean. In others, it resembles a crumpled hill. The Earth is not shifting dramatically. It is just technology revealing how lighting, perspective, and scanning geometry can turn a geological feature into a shape-shifting illusion. The water around the site, meanwhile, contributes its own challenges. The Baltic Sea is known for murkiness, low salinity, and complex layers of sediment that drift unpredictably. Visibility for divers is often dismal. Trying to examine something with precision in this environment is like trying to identify a piece of furniture in a dark attic while holding a flickering candle and standing in knee-deep dust. Despite all the evidence pointing toward geological origins, the anomaly remains fascinating because it sits in that rare scientific gray area, the zone where explanations exist, but none wrap things up neatly. It is probably a glacial remnant. It is probably a sculpted bedrock feature. It is probably not a spaceship unless aliens showed up with a vessel made of mismatched rocks and questionable aerodynamics. But the fact that probably remains in every sentence keeps the mystery alive. And maybe that is the real charm of the Baltic Sea anomaly. Not that it is alien, but that it reminds us how easily the ocean can trick our eyes, our instruments, and our assumptions. A rock becomes a riddle. A sonar blur becomes a global debate. A geological quirk becomes a cultural phenomenon. The anomaly sits quietly on the seafloor, not glowing, not humming, not transmitting signals, just existing, waiting for the next round of curious visitors to descend through the murky water and stare at it, trying to decide if they are looking at natural history or cosmic misdirection. If you could stroll across the deep sea floor of the Peru Basin, assuming you possess the kind of superhuman physiology that laughs in the face of crushing pressure, you would find yourself wandering through a landscape so strange and so unexpectedly tidy that it feels less like nature and more like a forgotten storage yard for metallic cobblestones. Scattered across the sediment, spread over kilometers upon kilometers, lie countless manganese nodules. Each one is a lumpy, misshapen sphere, roughly the size of a potato, though some are small enough to hide in your palm, and others are large enough to make you question whether the ocean has been secretly stockpiling cannonballs. At first glance, the scene looks almost whimsical, a plain of tiny, dark stones sitting neatly on the ocean floor, as though the planet tried decorating and then forgot what the theme was supposed to be. But once you realize what these nodules are and how astonishingly slow they grow, the whimsy fades into awe. A single manganese nodule may take millions of years to reach the size of a coin. Millions. This is growth so slow that continental drift looks ambitious by comparison. If human motivation followed the same timeline, we would still be waiting for someone to invent breakfast. These nodules are natural mineral accretions, layered composites of manganese, iron, and several economically valuable metals, including nickel, copper, and cobalt. They do not form from magma or rapid precipitation. Instead, they grow through a delicate process of chemical accumulation, where metallic ions drifting through seawater stick to tiny objects on the seafloor: shark teeth, fragments of shells, volcanic particles, slowly building layer upon layer until the nodule begins to resemble a geological jawbreaker. In the Peru Basin, where the surrounding water is rich in dissolved minerals and the sedimentation rate is extraordinarily slow. These nodules rest exposed on the seafloor rather than being buried. It is a perfect environment for them to grow undisturbed for eons, assuming nothing bumps into them, buries them, or tries to collect them for scientific study. What makes the Peru Basin particularly captivating is the density of these nodules. In some areas, they blanket the seafloor so thoroughly that the sediment is barely visible. Imagine walking across a beach made entirely of loose pebbles, except each pebble has a complex internal structure and a growth history that predates most modern species. The nodules vary in composition and texture. Some have smooth surfaces, others appear pitted or rugged, and their internal layers tell stories of shifting chemistry and environmental conditions that no human has ever witnessed. The surrounding environment is as surreal as the nodules themselves. The Peru Basin lies several thousand meters below the surface, in cold, still waters where light does not reach and temperatures hover near freezing. Above, marine snow drifts slowly downward, tiny specks of detritus that settle so gently that a nodule may wait centuries to be dusted with even a thin film. If the deep sea has a reputation for being dynamic and mysterious, this particular region is its quiet, contemplative corner, where change happens at a pace so glacial that glaciers would complain it is too slow. But this quiet aesthetic hides a scientific puzzle. Exactly how these nodules form remains only partly understood. Scientists know the ingredients: metal ions, a nucleation point, time, but the recipe's details remain evasive. Some nodules appear to grow primarily from chemical reactions at the seafloor, while others seem to accumulate materials from the water column itself. The Peru Basin hosts examples of both, suggesting that multiple processes overlap in ways that even seasoned geologists describe with phrases like complex interplay and "we need more data." Another mystery lies in the distribution of metals within the nodules. The layering is not uniform. Some bands are rich in manganese, others in iron, and still others in cobalt or nickel. These bands represent environmental shifts that occurred millions of years ago, but interpreting them feels like reading a diary written in a language no one speaks anymore, except the diary is shaped like a potato and weighs more than your laptop. Then there is the biological component. Yes, life is involved. Deep-sea microbes colonize the surfaces of nodules, forming invisible communities that may play a role in how metals accumulate. Some bacteria appear to accelerate the oxidation of manganese, effectively helping the nodules grow. Imagine microbes as tiny, extremely patient artisans, handcrafting metal lumps over geological timescales. These organisms survive on chemical energy rather than sunlight, scraping out an existence on mineral surfaces that would appear barren to any animal with a pulse. What complicates matters further is that the nodules do not simply sit passively on the seafloor. Slow-moving bottom currents occasionally shift them slightly. Burrowing animals may nudge them. Some nodules break apart over time, others remain intact for millions of years. Their distribution reflects a dance between geology, chemistry, biology, and physics, all unfolding so slowly it makes stop-motion animations look high-speed. Of course, because these nodules contain valuable metals, they have attracted considerable attention from industries hoping to mine the deep sea. The Peru Basin, with its dense fields, is one of the regions under scrutiny. This has sparked passionate debate among scientists and environmentalists, who warn that disturbing these ecosystems could erase not only life forms we barely understand, but also geological formations that took longer to grow than the entire history of human civilization. Removing a manganese nodule is not like picking up a rock. It is more like removing a fossil record that is still actively writing itself. And this is what makes the Peru Basin so mesmerizing. It is a place where time becomes almost incomprehensible, where growth is measured not in days or years, but in epochs. These nodules, scattered so casually across the seafloor, are among the slowest growing natural objects on Earth. They witness the rise and fall of species, the drift of continents, the reshaping of oceans. They endure while everything else changes around them. Standing in that basin, if one could, would feel like stepping into deep time itself, a landscape made not by eruptions or rapid upheaval, but by patience, endless quiet patience. And in that stillness, surrounded by millions of metal spheres older than entire ecosystems, you might finally understand that even the ocean's calmest corners hold mysteries that stretch far beyond human scale. If the ocean could prank humanity, the bloop would be one of its finest masterpieces. Recorded in 1997 by underwater microphones stationed thousands of kilometers apart, the sound was so loud, so distinctive, and so unsettling that it instantly ignited global speculation. Imagine a deep, echoing roar, low, rumbling, and rising in pitch, picked up across the Pacific like the world's largest creature clearing its throat. The bloop was not subtle. It did not whisper, murmur, or politely announce its presence. It roared in a way that said, "Hello, surface dwellers. I hope you enjoy mysteries you can't explain." For months after its discovery, scientists scratched their heads while the public joyfully skipped straight to one conclusion: sea monster. Not just any sea monster, an impossibly large one lurking somewhere beneath the waves, bellowing in a voice big enough to be heard across an entire ocean basin. Theories sprouted like overexcited kelp. A giant squid the size of a skyscraper? A prehistoric creature that missed all the extinction memos? Something with teeth big enough to floss whales? People were ready to believe almost anything, because the truth, whatever it was, hid in waters deeper and darker than imagination typically swims. The bloop was recorded by NOAA, the National Oceanic and Atmospheric Administration, using a network of hydrophones originally designed to listen for submarines. These devices spend their days soaking in silence, occasionally interrupted by whale song, cracking ice, volcanic rumbles, the clinking of shifting seafloor rocks, and once in a rare while, something like the bloop. When NOAA analysts first plotted the sound wave, even they were surprised. It did not match typical marine noise. It did not resemble machinery, and it had this almost organic quality to it, the sort of rising frequency curve usually associated with living animals. The catch? No known animal could produce something that loud. Blue whales, the largest creatures ever known to exist, could not come close. And that is when the mystery began to simmer. Scientists dove into analysis, comparing spectrograms, modeling acoustic behavior and trying to match the signature to anything recorded before. But the ocean is not an easy place to decode. Sound behaves strangely underwater. It bends, stretches, travels enormous distances, and sometimes merges with echoes from seafloor terrain. Untangling all that is like trying to identify a singer in a stadium by listening to a muffled recording made from a mile away. For years, the bloop remained without an official explanation. Meanwhile, the internet gleefully filled the silence with theories. Someone pointed out the eerie similarity between the bloop's pitch curve and the calling patterns of giant creatures from fictional horror stories. Others insisted this was proof that Megalodon, the 40-ton shark superstar of ancient oceans, had refused to go extinct out of sheer stubbornness. A few suggested extraterrestrial origins, because of course they did. The bloop became a cultural icon, a sonic riddle that encouraged everyone to peek nervously at the ocean with fresh suspicion. Then came the explanation. Kind of. NOAA eventually announced that the most likely source was not a colossal creature, but the cracking and fracturing of Antarctic ice. Massive icebergs breaking apart or scraping the sea floor can generate incredibly loud sounds, sometimes mimicking biological signatures. And indeed, the bloop resembled other icequake noises recorded later. The temperature shifts and melting patterns in the late 90s could have contributed to unusual resonances, sending the sound rolling through the Pacific with startling power. You would think this would solve the mystery neatly, but this is the ocean we are talking about. It hates neat endings. Even after NOAA's announcement, debates continued, and still do. Because the bloop maintains quirks that ice alone does not completely explain. Some acoustic experts argue the sound has harmonic qualities more typical of biological noise than geological events. Others counter with data on ice that behaves unpredictably, cracking in ways that mimic biological phenomena. The question lands not in a firm conclusion, but in a polite scientific shrug. Probably ice, maybe not. Please do not email us about sea monsters. But the emotional power of the bloop lingers. Part of that comes from its scale. Human hearing underwater is pitiful, but hydrophones reveal just how loud and restless the ocean truly is. Underneath the waves, Earth is constantly groaning, shifting, singing, cracking, thrumming, and occasionally hollering like something gigantic just stubbed its toe against the continental shelf. The bloop is a reminder of that soundscape, a reminder that the ocean is alive with noise we rarely think about. Another part of the fascination lies in what the sound represents, a boundary between certainty and possibility. Scientists can map the ocean floor, study currents, and model ecosystems, but acoustics remain one of the few tools that reach into the deepest, most inaccessible trenches. Hydrophones hear things our eyes will never see. And sometimes they hear something that makes everyone pause. Even if the bloop is just ice flexing dramatically, the mystery it sparked is valuable. It led to renewed interest in ocean acoustics, inspired new mapping initiatives, taught people about hydrophones, and sparked conversations about how little we truly understand about the deep. It revealed something delightful about us too, our eagerness to imagine the ocean holding secrets beyond our comprehension. Maybe that is not childish. It is curiosity in its purest form, and let's be honest, the idea of a sound so vast that it could have come from something alive, something massive, ancient, and unseen, tickles a part of the human brain that logical explanations cannot fully dim. Even seasoned scientists admit quietly and without giving fuel to conspiracy theorists that the ocean still holds surprises. Perhaps not skyscraper-sized monsters, but organisms we have not yet imagined, behaviors we have not observed, acoustic signatures we have not catalogued. So the bloop remains an icon not because it is unexplained, but because it symbolizes the ocean's talent for unsettling wonder. A single burst of sound rising mysteriously through the water, loud enough to be heard across the Pacific, strange enough to earn decades of fascination. Whether it was ice, geology, or some creature brushing against the microphone while trying to mind its own business, one truth remains. The ocean is always noisier, stranger, and more unpredictable than we expect. And somewhere out there, beneath crushing depths and endless dark, the water is still full of sounds we have not yet heard. Some ordinary, some startling, and maybe, just maybe, one or two waiting to become the next great mystery. Imagine descending into the ocean until the last rays of sunlight fade, not suddenly, but slowly, like a dimmer switch being turned by someone who is far too patient. You pass the surface shimmer, then the region where colors lose their identities. Reds vanish first, then oranges, yellows, greens, until everything is painted in deepening blue. Keep going a little farther and that blue begins to die too, dissolving into a dusk that does not care what time it is. Eventually you reach a place where light does not just weaken, it gives up entirely. Welcome to the midwater shadow zones, great swaths of ocean suspended between surface brightness and abyssal darkness, places so dim and so remote that visibility is measured in meters and mysteries in miles. The shadow zones are not the bottom of the ocean, nor are they the twilight region you might picture from underwater documentaries where shafts of light still reach down like inquisitive fingers. No, these zones sit deeper, in layers where sunlight cannot penetrate, and moonlight might as well be a rumor. Here, darkness is not an absence but an environment. Pressure increases, temperatures plunge, and the creatures that inhabit this space seem to have been assembled by a game developer who mashed together every strange character model they had left in the file. Biologists sometimes struggle to describe the midwater because it acts less like an ecosystem and more like a sprawling, drifting metropolis of weirdness. There is no seafloor beneath these animals to anchor their routines, no solid structure to hide behind, no coral neighborhood for stability. Everything floats, everything wanders. The inhabitants must adapt to a world where up and down are more conceptual than physical, where predators might come from any direction, and where food arrives unpredictably, like a cosmic vending machine that occasionally drops a snack but mostly ignores your existence. Because sunlight does not reach these depths, most organisms here rely on bioluminescence. Not gentle, twinkly bioluminescence like fireflies enjoy. No, this realm is illuminated by sudden bursts, strange streaks, glowing organs, and optical tricks that make the animals appear half translucent, half ghostly, and entirely unbothered by the laws of normal biology. Some species generate brief, bright flashes to confuse predators. Others produce slow glows to lure prey or communicate with potential mates in what must be the world's darkest singles bar. One of the hallmark adaptations of the shadow zones is what scientists call counter-illumination, a very technical term for the evolutionary version of wearing an invisibility cloak. Creatures like lanternfish produce light on their undersides that matches the faint glow from above, canceling out their silhouette when viewed from below. It is camouflage, but backward and luminous. Imagine walking through a dark room while wearing a t-shirt that projects an image of the wall behind you. That is how these animals hide. You cannot help but admire a creature that survives by turning into a floating optical illusion. But shadow zone inhabitants do not stop at invisibility. They take creativity even further. Some species develop elongated jelly-like bodies that seem to drift apart in slow motion, making them look as though they are glitching. Others have transparent skulls through which you can see their internal organs as clearly as a medical chart. There are fish with loose, dangling jaws, fish with eyes that point in two directions at once, fish whose skin is so black it reflects almost no light at all, making them vanish into the gloom as though performing a magic trick. The physics of the shadow zones also play a role in these adaptations. Because food is scarce, many organisms must conserve energy with a seriousness that would make a hibernating bear look hyperactive, swimming slowly, drifting, barely moving until absolutely necessary. These are survival strategies, not laziness. Muscles are reduced. Bones lighten or disappear entirely. Some animals replace structural tissue with gelatinous material that helps them maintain buoyancy without burning precious calories. This gelatin makes them look soft, squishy, and faintly uncanny, as though someone hit the low poly setting on their character design. Meanwhile, predators in the shadow zones evolve sensory adaptations that border on supernatural. Since they cannot rely on vision alone, many develop heightened sensitivity to vibrations or chemical cues in the water. Some have tubular eyes that amplify the faintest glimmer of bioluminescence. Others sport extended feelers that act like living antennae, sweeping the water for signs of movement. These predators drift silently through the dim water, operating in slow motion until the moment they strike, then exploding into speed with startling precision. There is also the matter of migration. Every night, countless organisms from the shadow zones rise toward the surface to feed in a commute known as the diel vertical migration. It is the largest synchronized movement of animals on Earth, repeated daily and yet almost entirely invisible to the human eye. Creatures ascend under cover of darkness to avoid becoming fish snacks, then descend again before dawn. Scientists describe this migration with reverence, acknowledging that the physics, timing, and energy budgets involved are mind-bendingly complex. The animals themselves do it instinctively, as though following an ancient unwritten tide schedule coded into their cells. Perhaps the most dramatic aspect of the shadow zones is the sheer emptiness. Not literal emptiness, plenty of life drifts through, but visual emptiness, with little light and vast distances between individuals. The space feels like an underwater desert. Days can pass without an animal encountering anything edible. This scarcity pushes evolution in unpredictable directions. Some species develop enormous mouths to increase their chances of catching prey, while others reduce their digestive systems to bare essentials to survive long periods of fasting. It is survival through minimalism, through efficiency, through techniques that make a Swiss Army knife look bloated. Yet despite all the strange adaptations, the midwater shadow zones remain poorly explored. Remote cameras capture glimpses, submersibles record occasional surprises, but the sheer size of this region, paired with the fact that it floats between worlds, makes it one of Earth's least understood habitats. It is not a place you can map in the traditional sense. There is no terrain to draw, no stable landmarks to reference. The shadow zones drift, swirl, expand, contract, and change with currents, temperature shifts, and storms happening hundreds of meters above. What we do know is this: the creatures here are some of the most inventive on the planet, designing themselves through evolution to thrive in perpetual obscurity. They are the ocean's glitchy characters, strange silhouettes flickering in and out of view, thriving in darkness with adaptations that feel almost whimsical in their ingenuity. And the shadow zones keep their secrets well. For every creature discovered, dozens remain unrecorded. For every adaptation explained, others remain baffling. It is nature's quiet, drifting frontier, a place where darkness births innovation, where life evolves not by shining brightly, but by mastering the subtle art of survival in the dimmest possible world. Long before human engineers dreamed up skyscrapers, the ocean built its own towering structures, massive white spires rising from the seafloor like an ancient stone metropolis. This is the lost city hydrothermal field, a place so otherworldly that even veteran scientists describe their first glimpse with the hushed awe usually reserved for standing inside a cathedral. Except this cathedral is alive. Its walls breathe warm, mineral-rich fluids. Its towers grow over millennia, and its architects are chemical reactions that operate with all the dramatic flair of a wizard conjuring stone out of thin water. The chimneys of Lost City are made not of volcanic rock, but of carbonate, a chalky substance similar to limestone. These chimneys can tower over 60 meters high, making them the tallest known hydrothermal structures on Earth. The moment their warm fluids hit cold seawater, minerals precipitate into delicate layers, slowly building spiraling, honeycombed walls. Viewed through the lights of a submersible, the entire field glows pale white or soft blue, as if illuminated from within. It feels like a place that should host dragons or scholars or possibly both. Yet it stands in total darkness, thousands of meters beneath the waves, hidden from the world for most of human history. What makes Lost City truly astonishing, though, is not the architecture, it is the chemistry. Unlike the black smokers found in volcanic hotspots, which spew dark, metal-laden fluids heated by magma, the Lost City vents run on a completely different engine. They tap into serpentinization, a process where seawater seeps into the mantle rocks below, specifically peridotite, and undergoes a transformation that releases heat, hydrogen, methane, and a cocktail of reduced compounds. No magma required. This is geology, operating on slow-burning magic, using chemical reactions rather than molten rock to sustain an entire ecosystem. The fluids emerging from these chimneys can reach temperatures of 90 degrees Celsius, not boiling but plenty warm enough to remind you that the Earth is always cooking something beneath the surface. These fluids are less acidic than typical hydrothermal vent waters, sometimes even alkaline, with pH levels that would horrify fish and amaze chemists. The chimney's interiors, meanwhile, act like elaborate plumbing systems, narrow conduits and branching chambers where fluids swirl and mix, shaping new mineral growth. Every vent is its own architectural experiment, sculpting itself molecule by molecule. In a way, the Lost City is a self-assembling fortress, constantly sculpted by chemical choreography. And within that fortress thrives life. Microbes cling to the chimney walls, feeding not on sunlight, but on hydrogen and methane. They are some of the most independent organisms on Earth, living without the usual requirements for life as we understand them. No oxygen? Many of them shrug. No organic matter drifting from above? They make their own. These microbes form vast biofilms, shimmering like thin ghostly curtains inside the chimneys. They break down minerals, build new ones, and essentially run a microscopic civilization powered by chemistry that would not look out of place inside a laboratory. Scientists adore these microbes because they might resemble the earliest ancestors of life on Earth, organisms that thrived long before the first photosynthetic creatures converted sunlight into energy. Back then, when Earth was young and chaotic, serpentinization could have created countless warm, chemically rich environments similar to the Lost City. It is tempting, almost poetic, to think that life's first spark might have ignited in places like this, quiet, dark, but vibrant with chemical potential. With that in mind, the Lost City becomes more than just a natural wonder. It becomes a window into ancient Earth. To explore it is to peer into a chapter of planetary history written in chemical handwriting. And the field refuses to be subtle about it. Some chimneys rise taller than human apartment buildings. Others form squat, rounded turrets. The largest tower, called Poseidon, stands so tall and imposing that if it were on land, it would instantly be turned into a tourist attraction, complete with overpriced gift shop. Yet for all its grandeur, the Lost City is astonishingly fragile. These chimneys grow slowly and can crumble easily. Their internal ecosystems depend on delicate chemical balances easily disrupted by physical disturbance or environmental shifts. Studying them requires precision, restraint, and a healthy respect for the possibility that one careless maneuver by a robotic arm could snap a structure that took thousands of years to build. And as if all of that elegance were not enough, there is a final twist. The lost city is not especially loud. Many hydrothermal systems roar and rumble with volcanic energy. Lost city murmurs. Its vents release fluids gently, more like warm springs than explosive jets. This gentler personality makes the site even more surreal. If black smokers are the ocean's industrial forges, noisy, smoky, chaotic, Lost City is its quiet, contemplative sanctuary, a monastery of stone pinnacles humming softly with ancient chemistry. The mystery deepens when you consider just how unique this field is. Scientists have searched for others like it and found none of comparable scale. Lost City stands alone, an isolated island of geological experimentation on a planet mostly shaped by volcanic heat. Why it formed here so dramatically remains only partially understood. The mantle rock beneath this location seems especially reactive. The fractures allow seawater to seep deeply. The chemistry creates exactly the right ingredients. But the puzzle is not complete, and Lost City does not volunteer its secrets easily. What we do know is that this place challenges our assumptions about where life can thrive, how ecosystems can form, and what environments might exist on other planets. Because if Earth can build a shining stone city in total darkness, powered not by heat from magma, but by reactions in the very bones of the planet, then who is to say what worlds beyond ours might hold? Lost City may not be home to dragons, ancient kings, or mythical libraries, but its walls contain something far more compelling, the blueprint of a world that existed long before we arrived, and hints of worlds we have yet to discover. For decades, the Bermuda Triangle has enjoyed a reputation as the ocean's favorite troublemaker, a triangular patch of Atlantic water that allegedly swallows ships, confuses pilots, and inspires more documentaries than most celebrities. People have blamed everything from magnetic anomalies to alien abductions to portals into other dimensions, as though the ocean wakes up some mornings and decides to be mischievous. But beneath all the folklore lies a geological landscape that is, in its own quiet way, just as dramatic as the legends. Because hidden below the waves are methane hydrates, peculiar ice-like deposits that can store enormous amounts of trapped methane gas until conditions shift and the seafloor suddenly releases it in a giant underwater belch. To picture methane hydrates, imagine crystalline cages of water molecules holding methane gas hostage under conditions so cold and pressured that this strange solid remains stable. These hydrates accumulate in sediments, forming pockets and layers across continental slopes. The Bermuda Triangle region sits on the edge of the North American continental shelf, where thick deposits of hydrates have built up over hundreds of thousands of years in deep, chilly sediments that behave like geological freezers. And as long as the freezer stays shut, everything is calm and quiet. But freezers have temperature settings, and Earth is not always consistent with its thermostat. When currents shift, When underwater landslides occur, or when the seafloor warms by even a few degrees, methane hydrates can destabilize, and destabilization is not subtle. The solid hydrate begins to break down, releasing methane gas that suddenly expands, bubbles upward, and alters the density of the water above it. If the release is large enough, the water column becomes frothy, full of bubbles, churned like a giant carbonated drink. Ships unfortunate enough to be floating above a major release could, hypothetically, lose buoyancy as the water becomes less dense, causing them to sink alarmingly fast. To be clear, this is not the ocean maliciously pulling a trapdoor trick. It is geology doing its thing, occasionally with theatrical flair. Imagine the seafloor sighing after holding in gas for millennia, and the ocean responding by briefly forgetting how water is supposed to work. Methane eruptions are not everyday occurrences, and large-scale ones are rare. But the physics behind them is real and well understood. They have happened in other regions of the world, leaving behind pockmarks on the seafloor, giant craters where the hydrate layers collapsed. Some scientists have pointed to these craters as evidence that similar events could take place in the Bermuda Triangle, even if no one has witnessed a modern eruption firsthand. But methane hydrates are only one part of this geological puzzle. The seafloor of the Bermuda Triangle is a dynamic, uneven landscape shaped by tectonic activity, sediment buildup, and subsurface fractures. Deep canyons cut across the continental slope. Layers of unstable sediment can shift suddenly, triggering underwater landslides that generate tsunami-like waves of displaced water. These submarine landslides can also jolt hydrate deposits, setting off chain reactions where gas pockets rupture and release in cascading bursts. The combination of shifting sediments, potential hydrate destabilization, and unpredictable seafloor terrain turns the region into a geologist's playground, fascinating, complex, and mildly chaotic. Add to this the strong currents flowing through the area, especially the Gulf Stream, one of the most powerful ocean currents on Earth. This current behaves like a watery conveyor belt, sweeping up debris, pushing warm water northward, and sometimes altering weather patterns. It creates conditions where storms can intensify quickly, compasses can behave strangely due to shifting magnetic fields, and aircraft can experience turbulence strong enough to make even seasoned pilots grip their controls with renewed appreciation for solid ground. When combined with the natural variability of the atmosphere, these oceanic factors sometimes create sudden squalls, intense downdrafts, and visibility changes, all without any supernatural involvement whatsoever. Still, the methane hypothesis remains one of the most eye-catching geological explanations for Bermuda Triangle mysteries. If a large bubble erupted and rose through the water column, its presence could temporarily disrupt both water density and air stability. A significant methane burst entering the atmosphere could, in theory, cause pockets of low-density air that affect aircraft engines or lift. While such events are not known to have caused documented accidents, the physics behind them remains compelling enough that researchers keep the idea on the table, not as definitive truth, but as a scientifically intriguing possibility. The challenge is that the Bermuda Triangle's ocean floor is not easy to study. Much of it lies under deep, sediment-heavy waters, and mapping it requires specialized sonar and remotely operated vehicles. Every expedition uncovers new geological features, ridges, pockmarks, sediment fans, painting a picture of a seafloor far more active than the quiet surface might suggest. Yet even with modern technology, the area remains underexplored compared to other parts of the Atlantic. The mystery, therefore, is not necessarily that ships disappear, but that the region is still full of unanswered questions simply because we have not looked closely enough. And perhaps that is why the Bermuda Triangle endures as a mythic space. The human imagination is most powerful where knowledge runs thin. When facts leave gaps, stories flow into them like seawater. But the real story unfolding beneath the waves is one of geology, chemistry, and physics, processes that unfold on scales far larger and slower than human lifetimes. Methane hydrates do not care about folklore. They respond only to pressure and temperature. The seafloor does not plot vanishings. It shifts and collapses as tectonic forces demand. And the ocean itself is less a stage for supernatural drama and more a vast system of currents and energy exchanges that occasionally produce conditions strange enough to make people wonder. So yes, the Bermuda Triangle may not hide cosmic gateways or interdimensional portals, but it does host a seafloor capable of burping with enough gusto to complicate maritime navigation. And in a way, that is almost as interesting. After all, nature rarely needs the supernatural to be astonishing. It manages just fine on physics alone. If you have ever procrastinated so thoroughly that you forgot what you were originally supposed to be doing, congratulations. You now share a personality trait with the whirlpools of the Weddell Sea. These enormous, swirling bodies of water behave as if they have no intention of going anywhere. They spin slowly, stubbornly, rhythmically, trapping the same parcels of water for years at a time, like the ocean's version of a stalled loading screen, known as maelstroms, a term that once referred to terrifying ship-swallowing whirlpools, but now politely describes massive rotating eddies. They are among the strangest and least intuitive phenomena in Antarctic waters. The Weddell Sea itself is already a place of extremes. It sits on the fringe of the Southern Ocean, bordered by ice shelves so thick they might as well be ancient fortresses built to keep out warm temperatures and anyone with a casual interest in comfort. The waters here are some of the coldest and clearest on Earth, home to deep currents that help drive global ocean circulation. It is a realm of silence, pack ice, and cold that does not politely nip your fingers, but hammers them with the enthusiasm of a vengeful freezer. Amid all this frozen majesty, the Weddell Sea's maelstroms form, giant, cylindrical eddies that can span tens of kilometers across and reach thousands of meters deep. They do not look like the dramatic whirlpools in pirate movies. There is no visible vortex dragging ships into chaos. Instead, these are subtle, steady, long-lived rotations created by the collision of cold Antarctic water with slightly warmer currents moving around the continent. When these water masses meet, The contrasts in temperature, density, and momentum cause the flow to curl inward on itself like a twisting ribbon, forming a colossal circular motion that remains remarkably stable. A maelstrom in this region is essentially a water trap. Once a parcel of water enters the swirling system, it can remain imprisoned there for years, cycling around and around like a lost tourist, too embarrassed to ask for directions. Some eddies drift slowly across the sea, while others stay rooted in place, pinned by underwater ridges, or guided by the shape of the continental shelf. Their persistence is so impressive that researchers sometimes refer to them as coherent structures, which is scientific shorthand for "this whirlpool refuses to quit." Inside these rotating giants, conditions differ from the surrounding waters in subtle but significant ways. Temperature layers shift, salinity patterns warp, nutrients accumulate or disperse in rhythms unique to each eddy, and because sunlight rarely reaches the waters trapped inside, these maelstroms become slow-moving laboratories of chemical and biological isolation. For the plankton or microbes living inside them, life essentially happens on repeat, round and round, year after year, in a drifting bubble of ocean with its own personality. What makes these structures especially compelling is how hidden they are. Satellite imagery can sometimes detect their signatures by looking at sea surface height anomalies, slight bulges or dips caused by rotating water. But the real action happens far below the ice-covered surface. To study them, oceanographers deploy floats that sink and rise like tiny robotic explorers, drifting into eddies and collecting temperature, salinity, and current data. Occasionally, these instruments get stuck inside a maelstrom for far longer than intended, unable to escape its hypnotic spin. It's the oceanographic equivalent of a research intern accidentally wandering into a revolving door that does not stop turning. The formation of Weddell Sea maelstroms ties into a much larger story: the global ocean conveyor belt. This massive circulation pattern moves heat, salt, and nutrients around the world, influencing climate, weather, and ecosystems. The sinking of cold, dense Antarctic water drives part of this conveyor belt. The maelstroms, by stirring water masses, concentrating cold layers, and occasionally expelling modified water into surrounding currents, play a role in shaping how this larger circulation behaves. A single eddy may seem insignificant, but multiply them across years, decades, and long Antarctic winters, and their influence becomes surprisingly weighty. One of the strangest aspects of these whirlpools is how they blur the lines between chaos and order. Surface currents in the Southern Ocean can be wild and unpredictable, especially when fierce winds whip across the ice. Yet beneath all that, the maelstroms maintain their patient rotations, unhurried by storms and largely unfazed by seasonal shifts. They are the introverts of ocean dynamics, quiet, persistent, doing their job without fanfare, while the rest of the ocean rushes around them in noisy turbulence. But these eddies are not just oceanographic curiosities. They have practical consequences. By trapping water for so long, they can influence how heat is stored in the Southern Ocean. They can isolate carbon-rich water, impacting how much carbon dioxide the ocean absorbs from the atmosphere. They even affect the distribution of nutrients that feed Antarctic phytoplankton, the microscopic plants forming the base of the marine food web. If a maelstrom decides to hoard nutrients instead of releasing them into circulating currents, the surrounding ecosystem feels the impact. And yet, for all their importance, we are still learning how these whirlpools behave. Their speed, depth, longevity, and internal structure vary widely. Some rotate clockwise, others counterclockwise. Some last months, others endure for years. Some drift slowly across the Weddell Gyre, while others remain locked in place, as if anchored to an invisible post. And because Antarctic conditions are unforgiving, gathering data is slow, rare, and often risky. Icebergs do not appreciate research vessels lingering too long. The weather does not offer apologies, and equipment has a bad habit of freezing, sinking, or being repurposed by curious seals. Perhaps the most poetic element of the Weddell Sea maelstroms is how unassuming they are. There is no dramatic surface display, no roaring vortex, no cinematic spectacle. Their power is quiet, their influence hidden, their persistence almost comical. They stir the ocean patiently, methodically, endlessly, holding water hostage in a giant, swirling loop until at last the current shifts enough to set it free. If the ocean ever embodied the idea of "I'll get to it later," it is here, in these slow-turning eddies spinning beneath Antarctic ice. And in the stillness of their rotation, they remind us that even the coldest, harshest places on Earth have rhythms, strange, subtle rhythms that shape the world in ways we are only beginning to understand. If Earth had a backstage area where it rehearsed all its most dramatic geological performances, the Tonga Subduction Zone would be the green room pulsing with heat, pressure, and a slightly chaotic sense of timing. This region, stretching along the southwest Pacific Ocean, is one of the most volcanically active places on the planet, a zone where the Pacific Plate dives beneath the Indo-Australian Plate in a slow-motion collision that has been running for millions of years. And like any long-running production, every now and then the cast delivers a performance so intense that the entire world leans forward in its seat. The Tonga Subduction Zone is home to a chain of underwater and partially emergent volcanoes. Many of them simmer quietly beneath the surface, releasing gas, rearranging seafloor topography, and generally acting like geological pressure cookers. Others erupt with more enthusiasm, sending ash plumes into the air, reshaping coastlines, and occasionally creating brand new islands, temporary ones usually, because the ocean enjoys reclaiming its territory with a firm and salty hand. But nothing in this fiery neighborhood compares to the event that occurred in January 2022, when the Hunga Tonga Hunga Ha'apai volcano erupted with such ferocity that it essentially announced itself to the solar system. The volcano sits mostly underwater, with only small fragments of land poking above the surface, two modest islands marking the rim of a much larger submerged caldera. Prior to the eruption, these islands had been slowly expanding as the volcano exhaled materials and reconfigured its upper slopes. But then the pressure beneath them reached a threshold that nature reserves for very special occasions. The resulting explosion was so massive that satellites observed a shock wave racing outward across the atmosphere in concentric rings. It looked as though Earth had been struck by a cosmic gong, and the entire sky was reverberating. Scientists studying atmospheric data later confirmed that the eruption produced pressure waves that circled the planet multiple times. These waves behaved exactly like the ripples that ring out when you strike a bell, except in this case, the bell was the atmosphere itself, and the mallet was a volcanic blast that released energy comparable to enormous nuclear detonations. The sound waves, some of which existed in infrasonic frequencies below human hearing, traveled farther than any acoustic signature recorded from a volcano in modern history. If the ocean were capable of raising an eyebrow at its own handiwork, this would have been the moment. But what exactly made this eruption so extraordinary? The answer lies in the peculiar design of underwater volcanoes. When magma encounters seawater, the interaction can be gentle if the water is shallow enough for heated steam to escape gradually. But when the water pressure is high, when the volcano sits deep enough beneath the waves, steam cannot expand easily, trapping energy and allowing pressure to build until the system becomes a geological pressure balloon begging to pop. The Tonga volcano's magma contained significant amounts of dissolved gases, and once the vent opened enough to depressurize the system, everything happened at once. The sudden flashing of water into steam produced an explosive force that dwarfed anything the volcano had previously demonstrated. Ash erupted into the sky so rapidly that it punched straight through the stratosphere, entering altitudes rarely touched by volcanic plumes. Lightning storms ignited within the ash cloud in numbers so staggering that satellites counted hundreds of thousands of flashes. Volcanic lightning forms when ash particles collide, generating electric charge. In this case, the cloud became a giant atmospheric spark machine. The spectacle would have been hypnotically beautiful if it had not also been profoundly alarming. But the underwater component of the eruption was just as dramatic. The seafloor shifted. Entire sections of the caldera collapsed or erupted outward. Pressure waves propagated through the water at speeds that startled oceanographers. Tsunami waves radiated across the Pacific, reaching coastlines thousands of kilometers away. Even the seafloor cable networks used to transmit data felt the shock, with a major communications line to Tonga severed by the force. Still, the Tonga Subduction Zone story is not defined solely by this eruption. The region hosts dozens of other volcanic structures, many of which exhibit behaviors that leave scientists alternating between fascination and mild existential dread. Some volcanoes quietly ooze lava flows along the seafloor, cooling into glassy pillows that resemble frozen balloons. Others release superheated fluids that transform surrounding sediments into strange, chemically altered layers. A few produce bubbles of volcanic gas that rise like boiling water from a pot, except the pot is the size of a mountain. One particularly intriguing feature of the region is its system of deep earthquakes, events occurring far below the usual depth for seismic activity. These quakes hint at complex interactions between sinking slabs of crust, rising magma, and the immense pressures of the mantle. The Tonga Subduction Zone seems to operate like a tightly packed orchestra of tectonic forces, each instrument playing loudly, unpredictably, and with no regard for human schedules. And while Hunga Tonga Hunga Ha'apai stole the spotlight, other volcanoes nearby remain fully capable of dramatic outbursts. Some have erupted beneath enough water that their explosions create glass shards known as pumice rafts, floating carpets of volcanic stone that drift across the ocean for months, carrying hitchhiking marine organisms on unintended global voyages. Others create hydrothermal plumes detectable from space, plumes so rich in minerals that they tint surrounding waters in ghostly hues. But the most humbling part of this entire region is how little we know. Much of the Tonga Subduction Zone remains unmapped. Many volcanoes have never been directly observed. The seafloor shifts too often, the water is too deep, and the conditions too harsh for frequent exploration. Our knowledge comes from glimpses, acoustic readings, satellite images, sudden bursts of seismic data, and the occasional expedition that manages to approach between eruptions. What we do understand, however, is that the Tonga region is a testament to Earth's restless interior. It reminds us that the planet is alive, constantly reshaping itself in ways both subtle and spectacular. And when one of its volcanoes decides to release centuries' worth of pent-up pressure in a single moment, the effect is not just local, it echoes across the atmosphere, across the oceans, and across our understanding of the natural world. The Tonga Subduction Zone is fiery, powerful, unpredictable, and profoundly humbling. A place where underwater mountains breathe steam, where eruptions redraw coastlines, and where, on rare occasions, the sky itself vibrates with the energy of a world that still has plenty of surprises left to unleash. If you were swimming off the coast of Yonaguni Island in Japan and happened to drift a bit farther than intended, you might suddenly find yourself staring at something that feels less like geology and more like the abandoned set of an underwater civilization drama. Giant terraces stretch into the blue like the steps of an immense amphitheater. Walls rise in perfectly straight planes, intersecting at crisp right angles that would make even the pickiest architect nod in approval. Pillars stand like weathered columns, slabs form ledges, platforms and corridors, and all of this is carved from a single enormous block of sandstone sitting 20 meters below the surface, as though waiting patiently for someone to explain why it exists. This is the Yonaguni Monument, one of the most debated geological features on Earth. Some people see it and immediately think ancient city. Others see a natural formation whose only crime is looking too orderly for comfort. And then there are those who decide it is both at once, nature providing the canvas, humans doing a bit of creative chiseling, and time erasing the finer details until only the broad, confusing shapes remain. But the truth remains slippery, submerged in currents and speculation. The structure was discovered in the mid-1980s by a diver looking for hammerhead sharks, which must have been quite a surprise. One moment you're admiring sharks being their sleek, intimidating selves, and the next moment you are contemplating whether Atlantis had a branch office near Okinawa. When researchers explored the site, they found not just one odd formation, but an entire complex of them. Flat plains, geometric steps descending in near-perfect increments, and angular ridges that resemble the foundations of deliberately built platforms. The largest section, sometimes called the main terrace, is massive, about 150 meters long and 40 meters wide. Its steps descend in broad, even layers, as if carved by a gigantic stone mason with a deep love of symmetry. Some divers describe it as a sunken ziggurat. Others see a colossal bleacher, awaiting a long-forgotten audience of deep-sea spectators. It does not help that the visibility around Yonaguni is usually excellent. The sun streams through the water, illuminating these strange edges and making everything look sharper, more deliberate, more suspiciously intentional. But geology has a sense of humor. It loves to produce shapes that trick the human brain. Sandstone, the rock comprising Yonaguni, breaks naturally along planes and joints. Under the right circumstances, wave action, earthquakes, and erosion can carve blocky, stair-step patterns that resemble architecture. Many geologists argue that this is precisely what happened here. The rock fractured along its bedding planes, waves undercut weaker sections, and gravity relocated the more fragile pieces. The result? A dramatic structure that looks like someone carved it, even though it may simply be nature's equivalent of doodling in straight lines. Still, not everything fits neatly into that explanation. Some features at the site look disproportionately regular. A smooth triangular platform, a massive vertical wall, a series of parallel grooves that appear etched rather than worn. There is even a formation known as the turtle, a stacked collection of curved slabs that looks uncannily like a carved sculpture. Though skeptics point out that humans have a tendency to recognize shapes in practically anything, including clouds, toast, and spilled coffee. One of the most discussed sections is a stone corridor that resembles a hallway. Its sides are sharply defined. Its path feels linear in a way rarely seen in purely natural structures. Then there is the so-called gate, where two upright slabs create an opening that, if found on land, would immediately be called an entrance. These elements give the entire complex a sense of order and design, fueling theories that Yonaguni may once have been above sea level, shaped intentionally by humans thousands of years ago before being swallowed by rising seas. If that were true, it would mean the structure dates back more than 10,000 years, placing it firmly in the era when humans were more concerned with not starving than with constructing seafloor condos. Some argue that this possibility is precisely why archaeologists hesitate to endorse the human construction theory, not because it is impossible, but because it would rewrite human history in bold, dramatic strokes. Others counter that early cultures did indeed develop sophisticated stonework, pointing to Neolithic monuments around the world as proof that ancient people could not have built this is an underestimation of human creativity. A particularly interesting twist is that Yonaguni sits in a region heavily shaped by tectonic activity. Earthquakes regularly rattle the area, and the rock layers are already predisposed to break along geometric lines. Some scientists propose that many of the sharp edges were enhanced by seismic shifts, creating the illusion of fine carving. In this view, nature built the basic shape, and earthquakes added the finishing touches. Cosmic collaboration, but without the need for ancient architects. But even if Yonaguni is entirely natural, it remains extraordinary. Most underwater rock formations do not look like architectural diagrams brought to life. They do not produce staircases 50 meters wide. They do not form blocky towers that stand defiantly amid currents. Yonaguni is unique not because it must be artificial, but because it occupies a rare sweet spot where geology and imagination overlap so perfectly that one cannot help but wonder. And really, that is the monument's greatest gift. It invites curiosity. It pulls divers into long discussions. It challenges assumptions about time, erosion, and the limits of ancient engineering. Every theory, natural, human-made, hybrid, reveals something about how we interpret patterns, how we crave explanations, and how the ocean still manages to surprise us with shapes that feel like puzzles waiting to be solved. The Yonaguni monument may never reveal a definitive truth. It may remain one of those places where certainty dissolves as quickly as disturbed sediment. But perhaps that is appropriate. Some mysteries thrive in the space between science and story, hovering right where the tides of imagination meet the bedrock of reality. If you could hover in a submersible somewhere in the deep ocean, far below the level where sunlight dares to wander, and turn off all your lights for a moment, you might expect pitch-black stillness. The kind of quiet, unmoving darkness that feels ancient, undisturbed, and almost frozen in time. But then, out of that silence, something would begin to move. Slowly, smoothly, like a shadow, deciding it no longer wants to stay put. A dense ribbon of darkness would slide past your window, flowing with weight and purpose. Not a creature, not smoke, not even a typical current. This is something stranger, a blackwater river, one of the deep ocean's quietest but most powerful sculptors. Blackwater rivers are not rivers in the usual sense. There is no riverbed, no banks, no gurgling surface ripples. They are underwater currents, so laden with particles that they move like liquid mud suspended inside liquid water, forming long, continuous, smoke-like streams. These currents can stretch for hundreds of kilometers, hugging seafloor contours, dipping into valleys, rising over ridges, and twisting through submarine landscapes with all the confidence of rivers that know exactly where they are going. If normal ocean currents are breezes, blackwater rivers are freight trains. The reason they appear so dark is density. These flows carry enormous loads of organic matter, plankton carcasses, mineral grains, detritus from upper waters, and microscopic leftovers of marine life's daily dramas. Every particle suspended inside acts like a tiny shade, absorbing what little light filters down from above or reflecting it in unpredictable ways. Taken together, they transform the current into a shifting ink cloud, an underwater storm surge that looks too solid to be water and too fluid to be sediment. What makes these rivers extraordinary is how quietly they operate. They do not roar or churn. They do not produce dramatic plumes like hydrothermal vents. They simply glide, slow, steady, silent. Many of them form as turbidity currents, triggered when seafloor sediment suddenly collapses and cascades downslope, gathering speed as it falls. Others arise from denser, colder water, sliding beneath lighter layers, pulling with it whatever particles happen to be drifting nearby. In either case, the resulting flow becomes a conveyor belt of material, sometimes soft and sluggish, other times surprisingly swift. These rivers play a secretive but critical role in shaping the deep ocean. As they move, they carve paths into the sea floor, scooping out canyons and depositing thick layers of sediment in basins miles away. Entire submarine valleys owe their existence to centuries of unseen blackwater movements. Geological maps reveal ancient channels hidden beneath layers of modern sediment. Fossil river tracks left behind by currents that flowed thousands of years ago, creating underwater landscapes that mirror the winding networks of rivers on land. But their influence does not stop at geology. They rearrange ecosystems as casually as someone reorganizing furniture. When a blackwater river sweeps through an area, it may bury organisms under blankets of sediment or uncover previously hidden habitats. Species in the deep sea often adapt to stable conditions, so when the river arrives, it can transform their environment in a single night. Some creatures thrive in its wake, feeding on the sudden abundance of organic particles delivered like an unsolicited buffet. Others vanish, overwhelmed or displaced. The river does not choose sides, it simply moves. There is something almost mischievous about how these currents behave. They can split into multiple branches, merge with others, or wander unpredictably across the seafloor. In some regions, they create sharp boundaries, one side of the river rich in nutrients, the other barren. It is the deep sea's version of a sudden neighborhood shift, except no one receives advance notice. Even researchers tracking these flows use words like slippery, elusive, and capricious in their reports, as though describing a pet that refuses to follow house rules. Because the deep sea is difficult to observe directly, much of what we know about blackwater rivers comes from instruments placed along the sea floor, sensors that record changes in temperature, density, and particle load. Sometimes those sensors capture sharp spikes in turbidity, moments when a river sweeps past and leaves a data signature as dramatic as a fingerprint. Submersibles occasionally glimpse these currents as they drift through the dark, revealing swirling edges, looping tendrils, and vortices that spin like pocket-sized whirlpools within the larger flow. But direct observation remains rare. The rivers do not perform on schedule. One of the most fascinating aspects of blackwater rivers is their role in transporting carbon. As organic particles drift down from the surface, blackwater flows gather them into dense streams and deliver them to the deep sea floor, locking carbon away for centuries or even millennia. This makes them quiet but influential players in Earth's climate system, moving carbon out of circulation and into long-term storage with a nonchalance that belies its planetary importance. If the climate system were a vast bureaucratic office, Blackwater rivers would be the employees quietly filing carbon paperwork while everyone else argues loudly in the break room. But these currents are not all slow, steady productivity. Sometimes they become violent. A large underwater landslide can trigger a turbidity current that rushes downslope at astonishing speed, up to 50 or 60 kilometers per hour, carrying boulders, sediment, and anything unlucky enough to be in its path. These events carve submarine canyons in real time. They can even snap undersea cables, which has happened repeatedly in multiple oceans. A cable might lie peacefully on the seafloor for decades before one of these rivers wakes up and sweeps it away like a piece of yarn. Despite their power, the rivers remain hidden from most human eyes. There are no swirling surfaces, no dramatic foam, just deep, dark currents slipping through the ocean's underbelly, redistributing life, sediment, and carbon with the understated efficiency of an invisible delivery service. And that quietness is what makes them so eerie. They move without warning. They transform landscapes without applause. They alter ecosystems without headlines. The Blackwater rivers are the deep sea's ghost architects, building, erasing, shaping, and sculpting, while the rest of the world has no idea anything happened at all. Hidden beneath kilometers of water, flowing in darkness so complete it becomes its own realm, these rivers remind us of something crucial. The ocean does not need sunlight to be dynamic. It does not need visibility to be powerful. Even in silence, even unseen, the deep ocean is constantly in motion, shuffling the pieces of its world with patience, mystery, and a touch of geological mischief. If you were an early sonar operator in the 1940s, staring at the ghostly glow of your instrument panel, you might have experienced one of the most unsettling moments in naval history. The seafloor suddenly lifting itself upward, not a little ripple, not a subtle tremor. The whole bottom contour on your screen rising several hundred meters like a sleepy giant stretching in its bed. Then, hours later, sinking back down again. It must have felt like the ocean was alive in ways no one had prepared you for. Some operators assumed their equipment was malfunctioning. Others wondered whether something large, very large, was pulsing beneath the waves. No one knew that they were witnessing one of the ocean's greatest daily migrations, carried out not by whales or squid or anything remotely majestic, but by a vast, shimmering community of small organisms moving together as though the ocean had given them a schedule. Today, we call it the deep scattering layer, an expansive, shifting zone composed of countless tiny creatures whose bodies scatter sonar waves like a living fog. The layer stretches across the world's oceans horizontally and vertically, a biological curtain suspended between about 200 and 1,000 meters deep during the day, and rising toward the surface at night in an enormous, synchronized commute. This migration is not optional for the creatures living within it. It is their way of surviving a world in which being seen is often the same as being eaten. The residents of this layer are not dramatic creatures at first glance. They include shrimp-sized crustaceans, delicate zooplankton, transparent worms, squid with bodies like ink-filled balloons, lanternfish with glowing organs, and gelatinous animals that resemble drifting fragments of moonlit jelly. Each organism is small, almost insignificant on its own, but together they form one of the largest biological structures on Earth, so dense and so reflective to sonar that early oceanographers mistook it for the actual seabed. Imagine millions upon millions of tiny creatures gathering into a horizontal cloud thick enough to imitate solid ground. It would be like birds flocking so densely across the sky that satellites mistake them for mountains. The deep scattering layer performs what is widely considered the largest migration on the planet. Every night, as darkness sweeps across the ocean's surface, the creatures rise toward shallower waters to feed on microscopic plankton. It is a coordinated ascent, timed to the fading of sunlight so precisely that scientists compare it to a choreographed ballet. When dawn approaches and hints of light return, the entire mass retreats downward again, dropping hundreds of meters in a matter of hours, slipping back into deeper, safer water before predators have a chance to capitalize on the crowd. This daily migration helps define the ecology of the midwater world. By moving up and down, these organisms transport nutrients, carbon, and energy between ocean layers in a cycle that influences everything from fisheries to global climate systems. When they feed near the surface at night, they ingest carbon-rich organisms. When they descend at sunrise, they carry that carbon with them, releasing it gradually as waste at depth. This process helps lock carbon away from the atmosphere, effectively making the deep scattering layer one of Earth's largest natural climate regulator day. Not bad for a community of tiny creatures whose main goal in life is don't get eaten today. But the deep scattering layer is more than just a biological conveyor belt. It is a fortress of sensory adaptations. Because these organisms live in a dim world, they rely on a remarkable suite of visual, chemical, and acoustic strategies. Some species carry onboard lanterns, bioluminescent organs that can glow or dim depending on whether they want to communicate or disappear. Others have bodies made of translucent tissues that refract incoming light, making them nearly invisible. Some possess enormous upward-facing eyes, tuned to detect faint silhouettes of predators above them. Others react not to light, but to pressure changes or subtle vibrations in the water, fleeing downward at the slightest hint of dangers. And danger is everywhere in the midwater. Large predators such as squid, fish, and diving mammals rely heavily on the scattering layer's migration to feed. Dolphins, for example, frequently hunt the layer at night, darting through its shimmering haze like aerial acrobats. Sperm whales dive to meet it during the day, holding their breath for over an hour as they navigate the shifting cloud of life. Even sharks venture into these depths, drawn by the immense buffet drifting slowly through the darkness. The layer itself, however, is startlingly unpredictable. It changes depth across seasons. It shifts locations based on temperature, food availability, and even the phase of the moon. In some regions, it splits into multiple layers, 2 or 3 overlapping strata that migrate independently like separate floors in a biological skyscraper. In other areas, the layer thickens into an almost impenetrable barrier of sonar reflective bodies, confusing submarines and researchers alike. Naval teams once dubbed it the false bottom, a phrase that perfectly captures both its mystery and its ability to make expensive equipment look foolish. One of the most captivating aspects of the deep scattering layer is how quiet it is. Not silent. Nothing in the ocean is truly silent, but quiet in rhythm. Its residents do not roar or rumble. They flicker, pulse, drift, and glow. Their migration is a movement of collective whispering, a tide of small bodies rising and falling without a splash. If the open ocean is a symphony of currents, storms, and biological noise, the deep scattering layer is its gentle crescendo, rising each night and disappearing each morning with understated grace. For scientists, this layer remains a tantalizing frontier. Its biological diversity is immense, yet only a fraction of its species have been formally identified. Many are too fragile to collect intact. Some disintegrate when exposed to pressure changes. Others evade nets with uncanny precision, slipping through mesh like living smoke. Cameras capture glimpses, but rarely full stories. We can detect the migration's movements, model its role in global systems, and theorize about its origins. Yet the full composition of the layer remains a shimmering puzzle, and that is the deep scattering layer's magic. It is massive, yet elusive, powerful, yet delicate, essential, yet mysterious, a moving boundary between worlds, a living horizon line where life organizes itself into a planetary scale breath, rising as night falls, sinking as day returns. What early sonar operators mistook for the seafloor was not rock, not terrain, not anything solid. It was life, in all its drifting, shimmering, quiet abundance. A reminder that even in the darkest waters, the ocean is full of motion, hidden rhythms guiding billions of creatures through depths where time is measured not by sunlight, but by the steady pulse of survival. If the ocean ever decided to take up geometric art as a hobby, the hexagons scattered across parts of the Atlantic seafloor would be its proudest portfolio pieces. These strange repeating patterns, some stretching across broad patches of sediment, look uncannily intentional, as though someone deep below the waves sat down with a compass and protractor and said, "Let's make something that will thoroughly confuse future scientists." And confuse them it has. For years, oceanographers have stumbled upon these formations during seafloor mapping expeditions, only to stare at the sonar images and mutter complicated academic variations of what on earth is that? The shapes vary in size, but many fall into consistent, honeycomb-like arrangements. 6-sided polygons pressed together in tidy arrays, mimicking the precision of bee architecture, but executed on a scale bees could never dream of. Some patterns cover only a few square meters, others stretch across hundreds. Their symmetry is what unsettles researchers most. Nature is excellent at producing chaos and excellent at producing order, but hexagonal repetition tends to appear only when physical processes fall into very specific patterns. Which raises the obvious question: what exactly is causing this underwater geometry lesson? One of the leading hypotheses involves sediment dynamics. In certain parts of the deep sea, the soft, fine-grained mud rests in a delicate balance, dense enough to hold shape, loose enough to shift with subtle currents. Under the right conditions, repeated flow patterns can carve out polygonal networks known as desiccation cracks, similar to what happens when mud dries and splits on land. But down here, nothing is drying. Instead, temperature gradients near the seafloor may create convection cells, warmer sediment rising, cooler sediment sinking, each cell nudging its neighbors until they settle into stable, hexagon-like compartments. It is the ocean floor equivalent of a lava lamp deciding to pursue geometry. Another explanation points to gas release, methane or other gases trapped beneath layers of sediment. When these pockets build pressure and begin to seep upward, they can reorganize the mud above them into patterned fractures. Picture a field of slow-motion bubbles trying to break through a thick blanket, pushing in ways that sculpt repeating shapes before the gas escapes. Over centuries, these fractures may widen, settle, and become permanent features. The result? A landscape that looks like a mosaic created by an artist who really loves regular polygons. But hold on, because the animal kingdom has entered the chat. Some researchers propose that bottom-dwelling creatures might be responsible. Certain deep-sea organisms, worms, echinoderms, and burrowing invertebrates are known to leave patterned trails or excavate sediment in repeated motions. If a population moves across the sea floor in large numbers, interacting with vibrations, currents, or chemical gradients, the result could be structures far more organized than any one creature intended. Think of it as biological graffiti. No single artist knows they are contributing, but together they produce a mural that would impress any passing submarine. Supporters of this biological theory sometimes point to the fact that hexagonal arrangements appear in other animal-made contexts. Pufferfish create intricate circular nests. Termites build ventilation systems with mathematically astonishing precision. Even microscopic organisms produce hexagonal surface patterns. The idea that deep-sea organisms might be shaping the sediment into geometric motifs does not sound impossible. It simply requires imagining a community of creatures choreographing a giant, unintentional art project thousands of meters below the surface. Then there is the idea that ocean currents alone might carve these designs. When steady flows interact with seafloor textures, pressure gradients can generate cellular patterns, smooth regions alternating with ridged ones, forming shapes that resemble honeycomb grids. This concept is similar to the patterns you might see when wind ripples across sand dunes, except underwater currents are more complex, shifting direction with depth and responding to temperature, salinity, and seafloor irregularities. These hexagons could be the signature of a stable yet little understood form of turbulence, a sweet spot in fluid dynamics where chaos briefly pretends to be organized. Of course, there is the most charming and scientifically useless theory. The ocean does it because it feels like it. After all, hexagons appear everywhere in nature when systems seek efficiency. Bubbles pack into hexagons to minimize surface tension. Basalt columns form hexagonal prisms when lava cools and contracts. Snowflakes branch into six-fold symmetry. When the universe wants a shape that balances stress, energy, and stability, it often reaches for the hexagon, as though it keeps a template close at hand. And yet, even with all these theories, none fully explains every observed pattern. Some hexagon clusters are too large for known convection processes. Others are too crisp to have been sculpted by burrowing animals. Some occur in regions where methane release is rare. A few appear in areas with strong currents. Others form in surprisingly stagnant basins. The ocean seems determined to avoid giving scientists a clean answer, preferring instead to toss out hints like a puzzle maker who enjoys watching people struggle. Part of the mystery stems from how rarely we observe the deep sea floor directly. Sonar mapping provides outlines but not fine detail. Remotely operated vehicles can approach these formations, but the sediment is so delicate that even a minor disturbance, a propeller wash, a landing skid, or a curious robotic arm can erase features instantly. When researchers finally manage to film the hexagons, the current may already have shifted them, or organisms may have disturbed them. Studying these patterns is like trying to examine footprints in soft sand while standing in the middle of a windstorm. What is clear is that the hexagons are not random. They represent processes we do not yet fully understand, shaped by the interaction of water, sediment, and perhaps organisms operating at scales too subtle or too slow for us to detect. They are quiet signatures of the ocean's internal logic, a logic we glimpse only occasionally in moments when the seafloor seems to reveal a secret. And perhaps that is the point. These hexagons remind us that the deep ocean is not static. It is constantly rearranging itself, sculpting patterns, erasing them, creating new ones, an ever-changing canvas where even mud finds ways to surprise us. The ocean does not need sunlight, storms, or dramatic volcanoes to be creative. Sometimes it simply draws shapes in the dark, letting the currents trace lines that would make a mathematician pause and smile. And somewhere in the Atlantic, beneath miles of water, those geometric whispers continue, shifting, aligning, dissolving, and reforming in quiet defiance of our efforts to explain them. If the ocean were a person, it would be the kind who smiles politely when asked a direct question, offers a cryptic answer that raises 5 new questions, and then slips away into the dark before anyone can ask for clarification. It is not withholding out of malice. Mystery is simply its native language. The deeper you go, the stranger it gets, and the stranger it gets, the more you realize that understanding the ocean is not a project with a finish line, but a lifelong relationship with a planet-sized enigma that refuses to be predictable. This is partly because the ocean is huge, absurdly, stubbornly, comically huge. More than 70% of Earth's surface is ocean, and much of it is deeper than most human engineering can comfortably visit. We have sent people to the moon with more ease than we have explored the average mid-ocean trench. Space, for all its distance, is at least willing to hold still. The sea shifts constantly. Currents swirl, storms rearrange the surface, and the pressure below grows so intense it can crush steel. Exploring the deep is like trying to read a book that keeps rewriting itself while also threatening to smash the reader. Even when we do manage to piece together answers, those answers rarely stand alone. Instead, they unravel into new threads. Discover a strange sound? Suddenly you are wondering about ice fractures, deep-sea vocalizations, and the acoustics of abyssal plains. Find an odd geological structure. Now you are debating ancient sea levels, tectonic processes, and whether erosion has been working overtime. Unlock the secrets of one ecosystem. You immediately realize you have no idea how it fits into the neighboring ecosystem, which is somehow weirder. Every solved puzzle reveals the outline of an even bigger puzzle hiding behind it, waving cheerfully. Part of the ocean's talent for secrecy comes from how interconnected everything is. A shift in one region ripples across thousands of kilometers. A deep eruption can alter chemistry in the water column that then affects plankton, that then affects fish, that then affects currents, that then affect climate. You fix one variable in your mental equation, and 10 others start raising their hands like over-caffeinated students in the world's most stressful classroom. The ocean does not do isolated stories. It does sagas, multi-part, deeply entangled sagas in which even the smallest character might turn out to be critically important. And then there's the way life itself behaves down there. On land, evolution is constrained by sunlight, weather, and the need for structural support. Underwater, especially in the deep, evolution is more like a jazz improvisation session. No one follows the sheet music. Animals glow, shrink, grow, distort, flatten, elongate, and simplify. Some feed on chemicals, some eat each other in the dark. Some drift like glass sculptures. Others camouflage so well they might as well be rumors instead of creatures. Understanding this biological circus requires more than taxonomy. It requires rethinking what life can be. Technology helps, of course. Modern submersibles, robots, sensors, and mapping systems have revealed more of the seafloor in the past few decades than in all of human history before that. But the ocean still resists transparency. Robots break, cabling snaps, batteries freeze, cameras fog. Pressure crushes instrumentation like an irritated hand smacking a fly. And even when everything works perfectly, the window of observation is tiny. A few hours of footage, a few samples, a few data points in a place that has existed for billions of years. Because the truth is, the ocean does not care about our timelines. It moves at geological scales, centuries, millennia, epochs. Currents take decades to complete their loops. Sediments build layer by layer over thousands of years. Creatures evolve in directions we do not anticipate, adapting to pressures and darkness and scarcity with strategies that often defy logic. We bring our anxious, fast-paced curiosity into an environment that measures patience in deep time. No wonder the ocean always seems one step ahead. But perhaps the biggest reason the ocean remains mysterious is psychological. Mystery is part of its identity. We look into the deep blue and expect answers, but what we receive instead is wonder. And wonder is powerful. It fuels science. It drives exploration. It keeps researchers awake at 3 a.m. staring at sonar maps while nursing a mug of coffee that tastes like exhaustion and hope. The ocean whispers, "Come a little closer. Look again." And we do, because humans are terminally curious, and the sea is terminally unknowable. Even the things we think we understand often surprise us. A volcanic vent that should be dead suddenly flares back to life. A species presumed rare turns out to be abundant in a place we never looked. A current that seemed steady shifts course. A sound we thought was biological gets reclassified as geological, or vice versa. The ocean is a planet within a planet, dynamic, secretive, improvisational, and delightfully unwilling to reveal all its mechanisms. And honestly, what would we do if it did? If the ocean suddenly confessed every secret, if every trench were mapped, every species catalogued, every anomaly explained, a certain spark would vanish. The sea's mysteries remind us that discovery is not a finite resource. It is renewable. Every expedition uncovers the unexpected. Every dataset contains a hint of something new. Every unanswered question demands a late-night debate and another pot of coffee strong enough to qualify as weaponized caffeine. So why does the ocean hide so much? Because it can. Because it has had billions of years to cultivate complexity. Because it is vast and deep and shaped by forces far older than humanity. Because its rhythms belong to a world we barely grasp. And because, perhaps in its quiet, swirling, unpredictable way, it understands something we often forget. Mystery is not a failure of knowledge. It is an invitation to look closer, to ask better questions, to explore again, to remember that Earth is still wild, still surprising, still capable of humbling us. And somewhere out there, in the shifting dark, another secret waits, patiently, silently, ready to give the next scientist one more reason to refill their coffee and dive back into the unknown.